Hello everyone. We are going to talk about self-tuning regulators. Our motivation for this study is to cope with a varying process or environment. What I mean by a varying process is, for example, a motor that operates for some times and then consequently the internal temperature may rise. You will find some parameters affected by the temperature rise, like for example the internal resistance of the windings or the viscosity of the oil. Another example of a varying environment would be, say, an aircraft flying at different altitudes, facing different pressure or wind speeds around it. So in these cases, we would like the controller to adapt, to have some algorithm to vary its parameters so that it can face the varying conditions. There are actually some assumptions that we are going to assume in order to design our controller. We are assuming that we have a system with unknown parameters, so the parameters are not known for sure. However, we will assume that either they are constant or vary very slowly. So these are basic assumptions in what we are going to do. Also, we are going to use what's called the certainty equivalence principle, and by that principle we mean that we are going to use some recursive estimator to estimate the unknown parameters. However, once the parameters are estimated, they will be used as if they were the true values of the parameters, and consequently the controller will be calculated based on that. So that means we are going to ignore the uncertainty in the parameters or the errors that may result from the calculations. Of course, this will have an impact on the performance of the controller, especially during the initial period when we initialize the controller, because there will be a significant difference between the true values and the estimated values from the parameter estimator. However, we are going to, according to the certainty equivalence principle, ignore these differences and use the parameters as estimated. Of course, that will give a sluggish response at the beginning, and this is called the learning period of the adaptive controller. And there are some studies to see or to find ways to cope with or to attenuate the effect of this initial sluggish response for the controller. However, this is not our purpose here. Now, we are going to classify the self-tuning regulators into two basic classes. The first one is called the indirect self-tuning regulator. In that case, we'll do the implementation in two steps. The first step is to estimate the process parameters, and that will be done using recursive least squares, for example. And once the process parameters are estimated, we implement the controller based on the estimates, based on the estimated parameters. So this is the indirect self-tuning regulator. The direct self-tuning regulator is based on parameterizing the control law in a form that can be used by the recursive least square. Consequently, the recursive least square estimator would actually produce directly the parameters of the controller. So here, direct estimation of the controller parameters. So that actually seems to be faster than the indirect self-tuning. However, it is not easy always to parameterize the regulator in terms of the controller parameter so that the recursive least square would use it directly. We'll see that later on. Now our objective is to design a self-tuning regulator for single input, single output systems, and the algorithm used will be the pole placement. By self-tuning regulators, it means that we would like our controller to have the capability of automatically tuning itself, so it would behave as if the true parameters of the system were known. And we are going to depend on a single input, single output transfer function of the system, so this is just for simplicity of presentation. And if we do that, then pole placement would be actually a general technique that can be used to design the control system. So I'm going to assume a plant, and that plant is single input, single output, as I mentioned. P and A here are polynomials in the say if we are talking about discrete time system, they will be polynomials in the shift operator Q. So the output of the plant, I'm going to call it say X, and X here refers to the actual output of the process. Like for example, if it is a motor and we are controlling its speed, so this will be the true value of the speed of the motor. However, in order to do feedback, we need to use some measuring device. So due to the measuring device, we'll have here some noise or bias imposed on the actual measurement. So the feedback signal will be taken from the measured output Y. Also, at the input of the plant, we will have two signals affecting the system. The first one would be the disturbance, and I'm going to give it the symbol V. And the second one is the control signal of the system. Now, I'm going to assume that the control signal is composed of two components. One of them would come from the feed-forward direction. So I'm going to assume here a transfer function T over R, where T and R are polynomials in the forward shift operator Q. The input to that feed-forward transfer function will be the set point. I'm going to call it UC. So this is the output of that block would be the feed-forward component of the control signal. And another component will come from the feedback. I'm going to call that S over R. Again, S and R are polynomials in the in the time shift operator Q, and that will enter here as a negative feedback signal. So that would lead to the control signal U. So here, let me recall that UC is the set point. V is the disturbance, and N is the noise. Now, in order to guarantee the stability of this system, we should actually have all the internal signals bounded. So if we have a bounded input UC, bounded disturbance, and bounded noise, we have to guarantee that not only the output Y be stable, but also X, the true output of the plant, has to be stable, and the control signal also has to be stable. So in order to study this, let's write the equations that describe the different relations in this block diagram. We can calculate an expression for U, T over R times the set point, and this is the feed-forward component of the control signal, minus S minus over R times Y, and this is the feedback signal. Also, we can write an expression for X, the output of the true output of the process, as B over A times U plus V. And finally, the measured signal Y, that would be just X plus N. In order to find an expression for X, Y, and U, we can just rearrange our equations. I will give some numbers to the equations. So I'll call the first equation number 1, equation number 2, and equation number 3. I will rearrange 3 equations so that the input signals would be at the left hand side of the equations and the other signals will be at the right hand side of the equations. So I would write t times the set point equals ru plus sy, and b times the disturbance equal ax minus bu, and finally the noise equal y minus x. I will put that in the vector matrix form. So I will have here in the left hand side t u c b v and n is equal to some matrix times y x and u. So up here I will have s, 0 and r, and then 0 a minus b, and finally I'll have here 1 and minus 1 and 0. Now a nice feature about the polynomials is that you can deal with them the same way that we can deal with real numbers when we solve a set of equations, which means that I can find expressions for x, y and u just by multiplying by the inverse of this matrix from the left. So if we do that, we will get these expressions. Now the polynomial AC that appears in all the expressions is given by AR plus BS, and this is actually the determinant of the matrix. This is called the characteristic polynomial of the system. So if we would like to get the characteristic equation of the system, the characteristic equation would be AC equals AR plus BS equal to 0. That means if I'd like to study the stability of the closed loop system, I have to find the roots of the characteristic equation. A necessary and sufficient condition for stability is to have all the roots inside the unit circle for a discrete time system. So necessary and sufficient condition for stability. The roots of AR plus BS equals 0 are inside the unit circle, which is a circle that has a magnitude equal to 1. So now let's see how to design a pole placement controller. I'm going to assume, as I mentioned, a single input, single output system, and I'm going to assume that I have 0 noise and 0 disturbance. We will see later on how to modify the design so that it will be able to compensate for the effect of the disturbance. So if we have this setup with just a set point and feedback and feed forward components of the controller, then we can write the closed loop transfer function as y over u equals bt divided by AR plus BS. Now the design would aim at concluding the values of TR and S. So required to find the polynomials T, R, and S, such that the output input relation would follow some desired transfer function bm over am. So bm over am, you may think of it as like our reference model, and we would like the relation between the output and the input of the system to be similar to this desired reference model. So that means I can say that I need bt over ar plus bs equals bm over am. However, since these are two ratios, then I have to make sure first that I take into account the common factors that may appear in the numerator and the denominator of one ratio before I can say that the numerators in both sides are equal and denominators at both sides are equal. So now I'm first going to factorize the zeros of the transfer function of the real process into two components. The first one I'll call it b plus, and the second one I'll call it b minus. The first component is monic, and the word monic means that the coefficient of the highest order of, say, q or z is equal to 1, and this polynomial will contain the zeros to be cancelled. So if I have in the original transfer function some zeros that I'd like to get rid of them in the closed loop, then this will be components in b plus, while b minus will contain zeros to be retained. Obviously, b minus should contain all zeros outside the unit circle, and also likely to contain zeros that are close to the unit circle, because zeros close to the unit circle, if cancelled, they will lead to a control signal that shows some high frequency oscillations, as can be seen in the simulations. So anyway, if b plus is the factor that to be cancelled, it has to appear in the numerator as the denominator of the closed loop transfer function. That means that bt over ar plus bs must be rewritten as b minus times b plus t, and then b plus has to be a common factor in the denominator. A is actually the denominator of the original system. I cannot force it to contain b plus. So r is a design polynomial, and that can be forced to have b plus as a common as a factor. So I would write a as r dash times b plus I'll factor b into b plus times b minus times s. Now I can actually cancel b plus from both the numerator and the denominator, so I will get here b minus t over a r dash plus b minus s. Now this has to be equal to the reference model bm over am. But again, there could be some common factors in the left hand side of the equation in this part of the equation. There could be common factors. So if in the numerator and the denominator, so these two common factor has to appear also in the right hand side of the equation. So I would write then b minus t over ar dash plus b minus s equals bm times a naught over am times a naught. So now a naught is a factor added to the right hand side of the equation in order to account for any possible common factors in the left hand side. If that is satisfied, then I can write then that b minus times t equals bm times a naught, and a r dash plus b minus s equals am times a naught. From the first equation here, if I call this, say, equation number 4, and this is equation number 5, from equation number 4 I can conclude that t equals bm a naught over b minus. But since t is a polynomial, then it's better that I would take b minus as a factor in the proposed reference model zeros. So we select bm to be equal to b minus times b bar m, and in that case the polynomial t would be just equal to bm bar times a naught. So this is the first polynomial that I would like to design. In order to find expressions for r and s, I will consider equation number 5. In equation number 5, I have ar dash plus b minus s equals am times a naught. Okay, let me first re-multiply both sides of this equation by b plus, so that would give me ar plus b s equals am a naught times b plus. Now we can see that this is the characteristic equation of the system. So if we put that equal to 0, it means that also the right hand side of the equation would be equal to 0, and that means that the closed loop poles of the system will be at am times a naught times b plus equal 0. So the roots of b plus, the roots of this polynomial, which it's called observer polynomial, and this is a design polynomial that we'll see how to select it when we do some examples, and the roots of the denominator of the reference model. These are the closed loop poles of the complete closed loop system. Now let's go back to equation number 5 and see how to solve this equation for the unknown polynomials r dash and s. This equation actually, an equation in an algebraic equation in two polynomials, is called the Fontaine equation. However, before we solve the equation, we have to notice here that in the controller, I have two transfer functions which are s over r and t over r. And these two transfer functions have to be causal. And by causality, it means that the output of a certain transfer function shouldn't actually shouldn't depend on future values of the input. This could happen if we ensure that the degree of the numerator and the denominator of each transfer function are equal. So as a condition now, we'll assume that the degree of r equal to degree of s, and this is for causality. Okay. Also, the Diophantine equation actually would have a solution if we assume that the degree of s in this polynomial is less than the degree of a by 1. So if we assume that the degree of a is equal to n, so the Diophantine equation will have a unique solution if the degree of s equals degree of a minus 1, which is n minus 1. Okay, let me recall that I'm solving the equation ar dash plus b minus s equals a naught am. Now, in order to solve this equation, I have to find the degrees of the polynomial r dash, the polynomial s, and the polynomial a naught. Now, we have already agreed that the degree of s is equal to the degree of a minus 1 from here. So this is now known. The degree of r is equal to the degree of s. We have said that before. So the degree of r dash would be equal to the degree of r minus the degree of b plus. So if degree of r is n minus 1, that would be n minus 1 minus the degree of b plus. The degree of a naught can be calculated from the Diophantine equation here. If we notice that a times r would have a polynomial of the highest order in the left hand side of the equation, so that the order of that product should be equal to the order of the polynomial that results from the multiplication of a naught times am. That means that the two orders are equal, and consequently I would write that the degree of a naught equals to the degree of a plus degree of r dash minus the degree of am. So now, knowing the degree of r dash, s, and a naught, I would assume a certain polynomial a naught, because as I mentioned, a naught is actually a design polynomial. It's an observer polynomial, and the effect of the observer polynomial, as we have discussed before, it would contribute to the closed loop poles of the system. So for example, if I'd like to have the roots very fast, I would put that polynomial, all the roots of that polynomial at, say, the origin or close to the origin, so they wouldn't affect the other poles of the system. So anyway, I select once I know the degree of a node, I can select that polynomial, and then I solve the Diophantine equation for r dash and s. Once this is done, I can find the polynomial r, because r is equal to r dash times b plus. So solve this the Diophantine equation for r dash and s, find then the polynomial r. Now I have r, s, and t, so the design is complete. Now let me summarize design steps for pole placement. First, we are going to assume that we are given a certain reference model, so we are giving the denominator and the numerator of the required reference transfer function. We will start by factorizing the plant, the original system, into two components. The zeros that will be cancelled, and those will be in the factor b plus. Zeros to be retained, this will be in the factors b minus. We calculate the degree of the polynomial r dash, and that would be the degree of the polynomial a minus 1 minus the degree of b plus. The degree of the polynomial r is taken equal to the degree of the polynomial s, and that would be equal to the degree of a minus 1. Then we calculate the degree of the observer polynomial as the degree of r dash plus the degree of a minus the degree of am. Once we know the degree of the observer polynomial, we select the that polynomial, and typically the roots of that polynomial will be close to the origin. We solve the Diophantine equation ar dash plus b minus s equals the observer polynomial times the am, the reference model polynomial. We solve that for r dash and s. So once we get r dash and s, we can calculate r, and the polynomial t is calculated as bm, the zeros of the reference model polynomials, times the observer polynomial divided by b minus. We agreed that we will take b minus as a factor in the reference model, so that should cancel out, and we will get here bm bar times a naught as a solution for t. This completes the design, because now we have already t, we have r, and we have s, so that would complete our design. If we assume that we have, as an example, a second order system like this one, we can calculate y of t equals minus a1 y t minus 1 minus a2 y t minus 2 plus b1 ut minus 1 plus b2 ut minus 2. And then we can write this in the standard form phi transpose times theta, where the vector phi would be composed of yt minus 1 minus yt minus 1 minus yt minus 2 ut minus 1 ut minus 2, and theta would be composed of a1, a2, b1, and b2 transpose. So once we form this, this is the regressor, we call this regressor vector. Once we form the regressor vector, and we know that we need to estimate 4 parameters, we can run the recursive least square to get theta hat. Once we get the parameters a1, a2, b1, and b2, the estimated parameters, we can then carry out the algorithm of the pole placement, so carry all the steps of the pole placement in order to obtain the polynomials r, s, and t. So we find R hat, S hat, and T hat. Hat here is used to remind us that we are using the estimated parameters theta. So once we calculate these polynomials, we can calculate the control signal, because we know that the control law is given by RU equals to TUC minus SY. So from this control law we find U of T, and that what will be implemented to the process. And this procedure is actually repeated at every sample. At every sample we have to calculate a new estimate theta hat, update the values R and S and T, calculate the control signal, and so on. So this gives a general idea about how to implement a self-tuning regulator based on the indirect algorithm. We'll see some examples in the next piece of the lecture. Thanks.